Hi everyone, this is Amit Kirti here. In this video, we would like to look at Prim's algorithm. The items for the discussion are Prim's algorithm introduction, Prim's algorithm example, the Prim's algorithm itself. Then we will analyze the Prim's algorithm using the same example we discussed in 2. And then we will try to find the time complexity for Prim's algorithm. Now, Prim's algorithm is an algorithm that is used to find a minimum cost spanning tree for connected, weighted, undirected graph. I guess there are a lot of words here, so let's try to see. Now, this is a graph. This is connected because all the vertices of the graph have some edge connecting all of them. It is weighted because the edges that connect these vertices have number on top of them. For example, if these vertices were cities, then this means this is the distance between the cities. Or if these represent houses, then this means probably the length of the cable connecting these two houses. And by length of cable, I mean the digital broadcasting cable, or the cable that gives you the channels in the house. So the cable laying company would lay the cable from one house to the other. So this could represent the length of the cable connecting between these two houses and so on. This is undirected because you don't see any arrow marks on these edges, which means the length between A to B is same as B to A, or the length between B to C is same as C to B. So this is a connected, weighted, undirected graph. And our aim is to start from this and get something like this. Now this is a minimum cost spanning tree which is obtained for this graph. It is a spanning tree because it connects all the vertices without any loops. So the definition of a spanning tree is that it's a tree which has all the vertices and there is some edge connecting all of the vertices. Now the tree is called a minimum cost spanning tree because if you find out all the trees of this graph, which we will see in the next slide, this tree is the final result which has the weight as minimum. That is, if you sum up the edges in this tree, the total will be less for this particular tree. Now if we had this graph that we saw previously, and we used a brute force mechanism to figure out the spanning tree, and then we try to choose the smallest one, then we can visualize there are 16 possibilities out of this particular graph. So these 16 possibilities are shown here. So we will have to list out all the 16 possibilities and choose the one which is the smallest, which works out to be this particular case in this example. So this would be a brute force way of doing it, and brute force way works only if the number of cities or number of vertices are less. If the number of vertices keeps increasing, it will be 2 to the power of that value. So since there are 4 here, it would be 2 to the power 4, which is 16. So if I have 5 cities all connecting each other, then it would be 2 to the power 5, which is 32. And if it is 6, it will be 2 raised to 6, which is 64. So as the number of vertices increases, it will be exponential. So probably brute force way is not really a good way to do this. Now this is a practical example of how Prim's algorithm can be used. Let's assume there are a set of houses which are already connected by the cable guy, and this forms his cable network, and he has to lay cables in a new neighborhood. So now for him to connect to say this particular house, he has probably 5 options. He can lay the cable from this house to this house, or this house to this house, or this house to this house, or from this house to this house, and or probably this house to this house. So he needs to decide to lay the cable, and his criteria could be he should lay cable in such a way that the length of the cable is less, or probably the amount of digging that is required to connect to the new house is less. So Prince algorithm will help him to decide laying the which particular house is the best way to begin with and end with, so that he can lay the cable with minimum cost and minimum digging. Now let's try to look at Prim's algorithm with an example of a particular graph. Let's assume I have this graph with six vertices, and they are connected to each other by this graph. And my aim is to find out the minimum cost spanning tree. So let me just list out the vertices as it is. Now I have to start with some vertex. So let me pick A as my starting vertex. From A, the Prim's algorithm says our aim is final tree should have minimum weight. So let's start from A. So A has three edges, one of length 3 which goes to B, another of length 5 which goes to F, and another of length 6 which is going to E. So since the tree has to be minimum weight, I should logically choose an edge which has minimum weight. So the minimum weight edge is from A to B, which is of length 3. So now A to B has been selected, and then with A and B as the vertices in my kitty, I need to find out the next shortest edge from both these vertices. So if you look at this graph, from A I have already chosen this, so I have only two more left, which is 5 and 6. Now since B has also joined the bandwagon, I have two more new edges, that is B to C, which is 1, and B to F, which is 4. So I need to choose between 1, 4, 5 and 6, and logically this 1, which is connection between B to C, is the smallest. So I will choose 1 from B to C, and C gets added into our kitty. So now I have 3 vertices and 2 edges connecting them. So my next edge should be to the one of these 3 vertices from any of the vertices that I have already selected. So that is either B or A or C. So I need to find an edge which is shortest to one of the unvisited vertices from all the 3 vertices that I have visited. So if you look again at the graph, I have this and this 5 and 6 from A. From B I have 4 left over, and from C, the new vertex, I have 4 and 6. So I have 6, 5, 4, 4 and 6, and I need to choose one of the edges. So I have two options actually. The smallest ones are either B to F, which is 4, or C to F, which is 4. Now since alphabetically B comes first, I can choose B to F as my edge. I could have as well chosen C to F. So the new edge that has been added is B to F, which is 4, and F is the new vertex which has got added into our visited list. Now from A, B, C and F, I need to find an edge which connects to either E or D, which is smallest. So now I have an edge of length 6 from A to E and 5 from A to F, which is left. And from B, I don't think I have anything left because I have used both 1 and 4. From C, I still have 4 and 6. And from F, I have the value 2. So between 2, 6, 5, 4 and 6, 2 is the smallest. So I would naturally choose that, and I would put E into the kitty. So now I have A, B, C, F and E, and the only vertex which is left over is D. So if we look at backwards, that is if we look at D and see who all are connecting to D, 6 connects to D, 5 connects to D and 8 connects to D. So logically I should choose the smallest one, which is this FD, whose value is 5. So from all these vertices, the way to reach D is from F. So the FD is connected and the length is 5 and D is a visited vertex. So we have created a spanning tree using Prim's algorithm, and the algorithm which actually says from all the visited vertices, choose the edge which is smallest. So this gives us a minimum cost spanning tree. Now, if we were to list out the algorithm, so at a very high level view, you can see the algorithm as below. You can download the code from our website www.thinkaloudacademy.com. So here I will just try to explain the algorithm. So this is the algorithm, and this would be our graph which we saw previously. So we'll try to relate this algorithm to this graph. So VT in this algorithm represents the set of vertices that have already been visited, or we can say that the set of vertices which are already present in our spanning tree. ET represents a set of edges which are already visited or which are present in the spanning tree. And this for loop will loop through all the vertices which have not been visited so that we can connect them to the visited vertex and add them to the spanning tree. So let's start first. So these are the vertices in the graph. So initially this step says add vertex V0 to the set of visited vertex. So let me start with A. So this gets added to the set of visited vertices, and ET is the set of visited edges which I will set to null because I have not visited any edge. Then for I is equal to 1 to leftover vertices, I will try to find the minimum edge E between vertices such that V belongs to the set of visited vertex and U belongs to the set of unvisited vertex. Now, since we have started with A, the only vertex that has been visited is A. So V belongs to VT means A is the vertex which belongs to VT. So from A, try to find out minimum edge to all the leftover vertices here, that is V minus VT. So in this graph you will see that from A there are only three possibilities, so AB, AF and AE. So I will choose the one which is minimum, which is AB. So U in this case becomes B and V in this case is as usual A. So there is an edge UV which connects this is the smallest edge which connects A and B. So this is the edge. So we will add the new vertex U to visited vertex and new edge E to visited edge. So this edge is added to the visited edge list and this vertex U gets added to the visited vertex. So now VT has two vertices A and B, and ET will have the edge AB. So we will go up in the for loop and I becomes 2, and we will try to find a minimum edge from both these vertices. That's what it says here. Find minimum edge E between vertices V and U such that V belongs to VT and U is in V minus VT. So our VT has now two vertices. So try to find out minimum edge from these two vertices to the vertices that have not been visited. So in this case, it would be BC, which is 1. So from AB, the smallest edge is BC, which is 1. So what happens is this new vertex gets added to the visited vertex, that is the new vertex C gets added to the set of visited vertices, and the new edge BC gets added to the visited edge. So we will continue like this from A, B, C to get F, and then from A, B, C, F we get E, and from A, B, C, F and E we get this new edge D. So in this way we complete our graph by following this algorithm, and the final answer is this edge set ET, which contains all the edges of the spanning tree. Now the time complexity analysis of spanning tree says that if the graph is represented as an adjacency matrix, then the complexity of Prim's algorithm is actually vertex square of the vertices. So it's of the order of say n square kind of a thing. So if I were actually to represent it as an adjacency matrix, so if I represent the edges in the form of a matrix, then since I have to have two for loops to go through the matrix, the complexity is actually v square. But if you were to represent it, the graph in the form of binary heap and the list of edges in the form of adjacency list, then the complexity actually reduces to E log V. So this is Prim's algorithm, and I hope you liked the Prim's algorithm to find minimum cost spanning tree. Thanks.